I showed you some kind of a demo, right, where the UCS is optimal, but the issue is that it expands a lot of a lot of states. So this is from the UC Berkeley site. So this was the one, right? You wanted to start from the green point and go to the red. So the straight line path was the optimum path. But what UCS is doing is it's doing a lot of exploration. It's going around and around and around, and before it finally, figures out that this is the best path. So it's a lot of work, a lot of hard work being done by UCS. Okay, so is there something that you can do about this? Okay, so that's going to be the topic of this lecture. Okay, so all these methods, BFS, DFS, and the uniform cost search, they don't make use of any additional information, right? It's you have the actions, you have the cost of their actions, or you make use of just that, what you immediately get from these actions. So one is the costs, and you also know which state you're going to. So that's about it. It doesn't use anything more. So due to that reason, these methods are called uninformed search methods. Okay, so that's where we kind of ended in the previous class. And today what we're going to do is another set of methods which we call as informed search. Okay, so here the idea is that suppose you have some more information, right, about maybe how far are you from the goal state. Okay, so suppose somebody told you that, roughly, I mean, this may not be the exact distance or exact cost, but some sense, it's like a clue that somebody gives you. Okay, so if I give you some clues that, if you go to this state, then you will be this much far. If you go to this place, you're this much far from the goal state. Then can you do something better? Okay, can you reduce the exploration? Okay, so that is what is the topic of informed search. So what I've just taken here is an example from the Russell Norvig textbook. So here the problem is a navigation problem, and the idea is you want to get to. I mean, it's a map, right? These are all places, and you want to get from one place to another. Okay, so here in particular, what you want to do is you're interested in getting from Arad, this place, to Bucharest. Okay, and you want to find what is the best path. And all these numbers here on these edges, those are the costs. Okay, the costs of traveling from Arad to Sibiu, for instance, is 140. The cost of traveling from Timisoara to Lugoj, this one is 111. So is my cursor visible when I just move my pen this way? Now do you see a point or a dot or something?
Yes, ma'am.
Yes, ma'am.
You do. Okay, good. All right, so this is the framework. And so what you're additionally given is this. This is a straight line distance to each of these places, from each of these places to Bucharest. Okay, so this is the actual distance you traverse might be much more. Okay, because there'll be some curves and some winding paths and all that. But this, what you have is the straight line distance. So from Arad to Bucharest, if you just connect it with a straight line, how much distance would that be? That is 366. Now from so from Sibiu, if you travel to Bucharest, if it's a straight line, if you travel, that's kind of the shortest distance. I mean, if such a path is available, that distance would be 253. Okay, so this one. Okay, so those numbers are given to you. So these are in some sense what are called heuristics. Okay, so this is a heuristic. This is not the exact distance. It's a clue. Okay, so now if I told this, how would you go about it? Okay, so what is the most obvious thing to do? Right, so you're in Arad. So the problem is travel to Bucharest from Arad. Okay, travel to Bucharest from Arad. Okay. And yeah, so if you have these, so these are some functions. These are heuristics. So if you have these numbers, and what would be the most obvious thing to do? So now you're at Arad. Okay, so you're starting at Arad, and there are, three options, right? So either you could go to Zerend, so which is this place, or you could go to Sibiu, or you could go to Timisoara. I don't know if I have the pronunciations correct, but Timisoara, okay. Yeah, but anyway, you get the idea. So there are these three places which are adjacent to Arad. So one of these three places you can go to. Okay, so how would you choose which one to go? Right, for that you have these numbers here, right? So you know that somebody has told you, somebody reliable has told you that Zerend is about 374 kilometers away from Bucharest. Sibiu is where is that? This is 253, right? So 253 kilometers away. And Timisoara, this one is 329 kilometers away from Bucharest. So these are the distances to Bucharest from each of these. So which one would you choose?
Sibiu.
Sibiu, right? So this is like further going forward, Sibiu will be the closest. So you choose this. So you come here. Now, once you're at Sibiu, there are two options. I mean, there are four options actually. So you have Fagaras, you have this place, Rimniku will see. I really have no idea if I'm messing up the name of the place. But anyway, so one place with, Fagaras, Oradia, Arad, and Rimniku. Okay, Rimniku we'll see. Okay, so here these distances, Fagaras, the distance to Bucharest is 178. Okay, and this place is 193. Then we have Oradia, which is 380. And then we have Arad again, which is, it's even more far, right? Because you're going back to where you came from. So these are the four options. So from this, which one would you pick? Right? So you're at Sibiu and you have to pick one of these four places.
Fagaras, because it's the closest to Bucharest.
It's the closest. So you'll pick Fagaras. And now once you're at Fagaras, there are again two options, Sibiu or Bucharest. So Sibiu is again 253 and Bucharest is 0. Okay, so it's probably not visible. So Bucharest, the distance is 0 because you'll already be at Bucharest. So then you will choose Bucharest, right? Because you'll choose this route, right? Because then you will immediately reach there. So this is the path you would take. This is the most intuitive way to do it. And this is what is called a greedy best first search. Okay, so greedily you choose based on the heuristic. Okay, so here again, in terms of implementation, I mean, what I just showed you is, what you actually choose for exploration in some sense, but the implementation is exactly like how you do UCS, okay, uniform cause search. You push in, I mean, when you start from Arad, was there a question? I think, okay, some of the students are not able to access Wi-Fi and therefore they're not able to join the class. Okay. Yeah, that's fine. So they can catch up with the lectures later, right? And yeah, so this is kind of unfortunate, but yeah. Okay, so yeah, thanks for letting me know. Yeah, please let them know that they can approach me anytime if they want to clarify doubts. When they catch up with the material. Okay, so right now there are about 37 people. That's fine. Okay, so coming to this example, how you would implement this is exactly like uniform cause search, right? You start off at Arad, and here there are three neighbors. Okay, so you will push all of them into the priority queue, but it's just that the priorities will be given by the heuristic. Okay, so it's the same implementation as UCS because you want to ultimately be able to get to Bucharest. Okay, so it shouldn't be the case that, I mean, these are heuristics after all. So it shouldn't be that, you take some path and you don't get to Bucharest. So for that reason, what you do is you use the same algo as UCS, uniform cause search, but just that the heuristic gives you the priorities. Okay, so in UCS, what you used was the cost from the start state to a particular node. Right? Here, what you're doing is the cost from the next state, wherever you're going to go to till the end. Okay, that is a heuristic. It's not the exact cost, because you would not know the exact cost beforehand until you have traveled that path. Okay, so I hope this is clear, the how greedy best search works. So maybe you should also try, with the queue implementation, and see what how the queue states. How the queue looks at various iterations. Okay, so in this sense, this is going to be complete. You're definitely going to reach the goal, but is it going to be optimal or not? That's the question, right? So, what is your sense? Do you think this is going to give you an optimal path? Is it going to give you the shortest path to the goal?
Ma'am, I have a question.
Yes.
In this algorithm, so basically, we take the priority based on the heuristic cost, right?
Yes.
So could you just change the tab? I want to see the map. Yeah. So first we are at Arad, right? So
Right.
we always after pushing in, let's say the second one was CBU. So is it guaranteed that we will reach the goal state? Because if that is true, then we don't need to push the rest of the two uh, neighbors, right?
Yeah. So it is not. Yeah. So that is. That's exactly the reason why we use the queue. It's not guaranteed that for every problem you will reach the goal, because this is after all a heuristic that's telling you. So it could be that there's actually no path here, but it's just given you some estimate, right? Some estimate is given, but maybe there is really no way to reach Bucharest through this path, right? Maybe you have to actually go a little longer to reach Bucharest. Okay, but the heuristic is giving you this, so you're just trying to follow the heuristic, but sometimes maybe that will not guide you properly enough to reach the goal, right?
Yes.
So that's the reason why you're still you're taking the safe way out, and you're pushing all the adjacent states also, so that if you go along this path, and finally if it happens that you don't reach the goal, you can still backtrack and then choose the next path, and so on. Okay, you can choose the next successor, and so on. Okay, so that's the reason you do this. So yeah, I hope the algorithm is clear. Are there more questions? Okay, so I gather that the algorithm, everyone is clear with it. So maybe can you just type in the chat box if it's clear or not, or what's the thing? Yes. Yes. Okay. Okay, good. So it's a simple algorithm, right? You just pop from the queue based on what is the what based on the heuristic. So is this going to be optimal?
Ma'am, optimal in the sense, are you talking about the least distance? I mean, least shortest path?
Yes. So the lowest cost path, the set
Uh,
of actions with the lowest costs.
there is, I think, one more route that is, if we consider the weights, can you show the tab? Yeah. So from Arad to Sibiu, from Sibiu we can go to Rimni, that one, and that costs less than what the path we have followed.
So this would be you're
Like if
telling
I
about this path.
consider the paths on like the weights on the map, yeah, 80, 97, and 101, that
Okay.
total sum is less than 99 and
Right.
200.
Right, exactly. So that's exactly the thing. So, you're not guaranteed, right? This is not guaranteed to be optimal, right? So, what was going on here, right? You came to Sibiu. That was a right decision. From greedy, what you did is you came to Sibiu, and after this, because the heuristic told you that Fagaras is closer. So Fagaras was 178 versus Renew will see was 193. So because of that, you chose Fagaras. But actually, Fagaras was a little more far from Sibiu. So this, there was a large cost here, and afterwards, maybe this was the heuristic told you that Fuggerus is cheaper later on. But actually this Rimni, who will see, was a cheaper way to go, right? So what can happen here is there might be some very costly operations in the beginning, and that might guide your search wrongly. For example, maybe you're like, it's again maybe a road example, where you're at this point, this is where you're starting and your goal is somewhere here, okay? And there is this intermediate path, and you can go here, and maybe there is a really long path like this, okay? On the other hand, maybe there is another path. This, let me label this point as A, and there's a point here which is B. Okay, so the heuristic, in terms of the heuristic, if it is just the straight line distance, A is actually closer to the goal, right? But B is actually much farther. So you will never prefer it, but it could be the case that from B there is there's a shortcut there. Okay, so it's the road is better maybe. Okay, so that information is not taken into consideration here for greedy. So that's what is happening here. Though A is, as it's closer as per the heuristic, but and it's also like it's closer to S, and it's also as per the heuristic, the straight line distance is less, but the overall global best would be to go to B and then go to the goal. Okay, so these are some issues with the greedy method. So one thing is that it's not going to do too much exploration if it reaches the goal. If there's a way to reach the goal quickly, it will do that. It will not explore too much, but it may not be optimal. Okay, so let me just write down a summary of this. So you had, on one hand, you had UCS, okay, and here you have greedy. So greedy is an informed search method, whereas uniform cost is uninformed, so you don't have heuristics. So what is going to happen is there are different features. So you have optimality and exploration. Okay, now UCS does too much exploration, so let me just say it's too heavy. So greedy, it will not much. It won't do much exploration. I mean, provided the heuristic is fine and you can reach the goal, it's not going to do much exploration. Whereas UCS is optimal, but greedy, you can't guarantee this. Okay, so you can see where I'm getting to, right? So what we want really is this property of UCS, this is desirable, and this property of greedy, which doesn't do too much exploration. Okay, so some kind of heuristics search, which can, I mean, of course, when you want lesser exploration, you need to go for heuristics. Okay, we cannot do that without any heuristics. So how can you improve this? How can you improve the greedy approach? Or what is an alternate approach to achieve this? Get optimal, but also not do much exploration. Okay, so that's going to be the next algorithm we will do. So this is one of the very well-known applications in AI, and today it's being used in several applications like video games and in speech analysis and so on. Okay, so this algorithm is called A star. Okay. Now, what you do here is it's in some sense a combo of both. In UCS, what you did was you looked at the heuristic or whatever you used in the queue. So let me also just write that. Let's move this a little down. Okay. So here, since the implementations were the same, I'm just writing what the priority function you used was. So in greedy, it was the heuristic. So I'll just call this heuristic with the name h. Okay, so h of whatever some state. Okay, so that is what you would use for greedy. And in the priority function, what you used is the total overall cost, right? So overall cost from start to a state. From start to a state. So I'll call this function as g. Okay, so g of the new state. So this is G of state. Okay. So what A star is going to do is it's the same, again, the same algorithm, the priority queue you use, but instead of, like the priority function being either of these, what you will do is the heuristic function here, so f of n. So this is the priority function used here. The priority function is just g of n plus h of n. Okay? It's just the sum of these two. Okay. So let's just see a demo of this. Maybe like I'll just take a simple example and show you what, one run of A star. Okay. So this n is the states. Okay. So yeah. So let me just write an example here. So you have S, you have A, B, and suppose this is a simple example. And suppose these costs are 2. This is 2, this is 2, and this is 3. Okay. And now for the goal state, let me also write what the heuristics are, the edge function. So the edge function for the goal state is always, it's typically 0, right? I mean, there's no reason to have something other than 0 here. So let this be 0. And for A, let the edge function give you 2. And for B, suppose the heuristic is telling you it's just 1. So 3 is the actual distance to the goal, but the heuristic tells you it's 1. And for the start state, okay, it doesn't really matter, but let's say we have it. So h is 3. Okay, so these are the numbers. I will tell you what the g evaluates to as we go along. It's just the overall cost from the start state. So let's begin. So initially in the queue, what you're going to have is just S. Okay, and S has G of S. So that is how far are you from S. So that is 0. And H of the start state. So G of S plus H of S. That's what you're going to push in. And G of S is 0. H of S is 3. Okay, so this value is going to be 3. And the sequence is just S. So I'm just pushing in the sequence of states. Okay, I'm not explicitly defining the actions here for now. Okay, so this is the queue at the start. Okay, so the heuristic plus this G is giving you a value of 3. And now this is the only element in your queue. So you're going to pop this out. Okay, and you're going to say that, this is visited, S has been visited. Now there are 2 neighbors, A and B. So what you're going to push in is A. So what you will have is G of A plus H of A. So now G of A is, G of S, which was 0, plus this 2, okay, from the whatever is written in blue. Okay, so that is the actual cost of reaching A. So G of A is 2, and H of A, you're given that it's 2. So that is the one which is written in red. So this is 2. So overall, you have a value of 4. Okay, and the path is just SA. Okay, so this is one entry in your queue. Now the next entry is B. So that's the other neighbor. And here you have, what is it going to be? Can you tell me what is G of B plus H of B? Can you tell me what is G of B?
2.
2.
Yes, 2, right? So it is the 0 plus 2. And what is H of B?
1.
1. So overall, this is 3, and the path is SB, right? So this is your queue. And now the cheapest one is B. You're going to remove this element, and you will mark B as visited. Okay. So what you're going to have is, now the third iteration, you have A. So the heuristic, the total priority is 4, and you have SA. And now you have the neighbors of B that you're going to push in. So here there's a goal state. Okay. And so you need this function, right? G of capital G plus H of capital G. So based on whatever you've seen so far, what's it going to be? So what is G of the goal state at this point?
5.
5, right? Because it's from B, whatever the extra cost. So till B, it was 2. So this is going to be 5 plus what is h of g?
0.
0, right? So this is going to give you 5. And the path is what?
Part H,
SBG.
SBG.
SBG, right? So this is the next step. And now here again, you're going to, okay, so you have 5 and a 4. So this is going to get popped out. Okay, now, so A is going to get marked as visited. And now A has a neighbor, A's neighbor is also G. So what you're going to do is, if you will see this total cost, and if there is, if it is less than the current priority, you're going to update. Okay, so now the revised value of G plus H of G, what is it going to be? So H of G is anyway 0, that we know. And what is small g of G? Now you're going from A,
4.
right? 4. Okay, so this is going to be 4. And so you're going to update this goal state to have this total priority. And the sequence of actions also, you will update it to SH. Okay. And now this is only thing that is left here, and you will pop it and you will reach the goal state. Okay. So this is, I just showed you a demo of this. Now in this example, okay, the advantages are not very clear because you are still going to explore you're going to explore A, B, all the states, right? It's a small example. It was just meant to show you how this works and how you compute this G and H functions. So let me just show you one example in Pac-Man. Okay.
Excuse me, ma'am.
Yes.
Ma'am, can you please explain again like what the heuristic function represents?
Yeah, so I will come to that. I will explain it for each of these applications. So I think Tushar's question, it leads to, I think it stems from the fact that this is very sensitive to the heuristic, right? If you don't have this heuristic, it's exactly the same as UCS because UCS only uses this. Or if you set H as 0 everywhere, you're going to get back UCS. So yes, as you must be thinking that this heuristic function is a very crucial part of A star. So I will come to that in some time. It's just for our understanding temporarily, it is like it's a clue that somebody gives you about how far you are from the goal state. So in this example, we have B is actually the distance is to the goal as 3. Okay, but the heuristic tells you the distance to the goal is just 1. So yeah, so h of n is it's an estimate of how far you are from the goal, of how far you are from the goal. Okay, so this is, it's not equal to, it need not be equal to the true distance. Okay, or it need not be equal to the true cost. Okay, so we will go into a little more details about how you can get this. Let me just show you an example in Pac-Man. Okay, so for example, in Pac-Man, we have this this board where you have these kind of paths, right? Like there's some walls in between, and Pac-Man can go. If it has to go from this point till here, it cannot just directly jump till here, right? There is a path it has to go. Okay, so one possible heuristic function that you can use here is what is called the Manhattan Heuristic. Okay, so let me just say that anyway, so because I'll show you the demo. So Manhattan distance. So what this means is, so all of you, I guess, know the Euclidean distance, right? So let me just write that also. So Euclidean distance is the straight line path. So if you're at A, and so this is x1, y1, and what you're having here is x2, y2. So the Euclidean distance is always your usual notion of distance, right? You have x2 minus x1 square plus y2 minus y1 square. Or in higher dimensions, you can again adapt this. You'll have many more summations. And so this is what is the usual notion of distance. Now, Manhattan distance is just going to tell you like how would it be if you traveled along this path. Okay, so instead of jumping directly in the straight line distance, if you went all the way till this end and jumped down, what is the distance? So this would be x2 minus x1 plus y2 minus y1. Okay, so absolute value of this difference. So that is this length. Okay, so for the Pac-Man example, I mean, this is a reasonable heuristic to use because you know for sure that you're not going to travel, directly in this manner. But yeah, so if there were no other, I mean, if there are no blocks here, maybe you will. This is what at best you would do. Now, if there is a wall blocking you at this point, then again the distance will increase. Okay, so this is some estimate of what you think might be the distance. Okay, so with this, I'll just maybe show you this demo of what happens in Pac-Man. So I will use the small maze version. So, I mean, you will also do this in your lab. You will see this, but it's just to give you an illustration. So here I'm going to use a star. I guess it's fine. Everything else is the default one, so should be okay. Did I? Okay, I think I had to give a, okay, so the heuristic was wrong. So you see, this is an issue, right? So the heuristic I used was something, it was a very, trivial heuristic, something like you just gave a 1 or something. So it will not help. So you have to do something else. So I have already, there is a Manhattan heuristic, which is there, and I'm just going to use that. Okay. So here you see the path it took. Let me reduce the frame time. Okay, so Pac-Man started here and it had to come to this point. Okay, and you can see that it's actually choosing the optimal path. Okay, it's doing some exploration. These red nodes are, these red regions are the regions which it explored initially. So it explored this region, it explored all this region. Some of these other regions it didn't explore, and it finally found this path. Okay, so this is actually the shortest path. So the search nodes, okay, so you can see here the number of nodes it expanded. So in the terminal, you can see this, the search nodes expanded was about 53 and the total cost was 19. Okay, so now let's just see in contrast what happens if you use UCS instead. So in UCS, there's no heuristic. Okay, so I'm just going to use UCS and small maze. Yeah, I think everything else looks fine. So let me first just run it quickly. So here you see, it's exploring everything, right? The frame time of, what is it, 2? Okay. Yeah, so you see the block, right? There are so many regions. It explored everything near this initially, and it also explored some other parts here. Okay, so these parts, actually there was no need to explore because the idea was to get to this part, the goal was here, so it didn't really make sense to go too far. Okay, so this heuristic also played a role. Like the Manhattan heuristic was a reasonable heuristic here. Okay, and so here if you see, this was uniform cost search and it expanded 92 nodes. If you see in the terminal, there were 92 nodes it expanded, 92 states it has visited. And of course, the total path, the final path returned was optimal. This was 19 and both returned 19. So this was UCS and this is A star. So both have returned 19. But, A star explored a little less. So it's 53 versus 92. Okay, so there are these examples which shows that, A star is helping, but yes, the heuristic is a very important part of A star. So let's just see some more issues in A star, or let's just try to understand a little further. Okay, so what's going on here? So before that, any questions on the demo or whatever I just showed you now? Somebody had typed. Okay.
Excuse me, ma'am.
Yes,
I have some doubt regarding heuristic values.
Yes.
Actually, heuristic value is like approximate value of cost from a node to a final state, right?
Yes.
So, ma'am, like how is a node given heuristic value, means how it is decided for a node?
Yeah. So this is actually one of the really crucial decisions that go on. So that it's very problem specific. Okay, so for each problem, whenever you're applying A star, you have to see like that. It depends on the application. There'll be some. I mean, like for these, for this map example, for instance, whatever I started off, right? I showed you this, this map example where you had to get from Arad to Bucharest. So here, this is actually a reasonable heuristic, like the straight line distance. Okay, so you can also try applying A star here and see what it gives. Okay, so I will leave that as an exercise. So you will see that this is a reasonable heuristic for this application, but maybe the straight line distance is not very good for the Pac-Man example. Okay, because in Pac-Man, already for sure that you cannot travel along the straight line path. So it's a combination of things like what do you know about the domain, right? And what is logical for the domain? That is something that you have to make use of to design good heuristics. In fact, we will also be doing like what are the things that you need to consider. There are some mathematical properties that these heuristics will satisfy. We will need to satisfy in order to ensure that A star is good. For example, I showed you, initially I gave a wrong heuristic, right? And A star didn't have much advantages from it. Okay, so that's why that's a very important thing. And under some conditions for the heuristic function, only then can you guarantee that A star is optimal. Okay, so much of the focus will be on designing good heuristics. Okay, so we will see this anyway. So we'll see one more example just to understand how the heuristic should be, and what issues can happen with with the heuristic. So let me just take one like small examples we will do. So this is a very tiny one. So S, so you have A and you have G. Okay, so just three states and just two parts. So so this is 1 and you have 3 and 5. Okay, so these are the actual costs. And okay, I interchange the colors, but okay, hope you don't get confused. So for the goal state, suppose I say H is 0, and for the state A, like say H is 6. Okay, and for the start state, it really doesn't matter because you're not going to use it. First, you're definitely going to pop out the start state, but let's say maybe it says it is 7. Okay, so here, let's just do the A star algorithm. So first S is going to get visited. So I'm just not writing the queue. So S is there. That's the first step. Now in the next stage, what you're going to push in is A and G, right? So A is going to get pushed in. And what is going to be the function? So it is G of A plus H of A. So what is this going to be for this example?
1 plus 6.
1 plus 6. So this is 7. And the path is SA. And so this is one entry in your queue. Now the next one is G. So what is going to be the value? The priority?
5.
5.
5, right? So this is going to be 5. And you have SG. Okay. So now what's going to happen? Your queue has these two entries.
Goal state will get popped out.
So this will get popped out and you will say G is visited, and the plan that you would have come up with is SG with a cost of 5. Okay, but here there is another path, SAG. The overall cost is actually 4, right? It's a smaller path, right? So here A star didn't give you the optimal, right? But what is going on? Why did this happen? Right. So the issue is, you would have guessed, it's because of this heuristic. Okay, the values, there's something wrong with these values that's causing this issue. So what is going on here is for the goal state, it's okay, H is 0, so that makes sense. Now for this state A, right? So actual distance from A to G is 3, but the heuristic is saying it is 6. Okay, so this is a problem, right? For the if the heuristic is going to exceed the actual value, then we are in trouble, because the way the algorithm works, it will not pick out this element first. It will there'll be other elements it will pick out which is cheaper. So that's an issue here. So what you want is the heuristic should be, this property that you wanted to satisfy is heuristic should be admissible. Okay, so what admissible means? So let me just write it. So admissible if h of n for any state n should be less than h star of n, where h star is the true distance or true cost from n to a goal. And this should be true for every state n. Okay. Yeah, so now you don't know what is h star n. How do we come up with this? Okay, so that is a valid question to, if you're thinking that. Yeah, so that's where the domain info helps. Like, so this boils down to what I was telling for Pac-Man. So here you know that, the best possible distance from, the rightmost corner to the leftmost bottom corner, that has to be the Manhattan distance, right? Because, it is always going to have this kind of a path, right? So this is a reasonable distance here. Now, similarly for this example, the map example, the straight line distance is always going to be an underestimate for the actual distance. So here also the Euclidean distance is a good, heuristic. Okay, so like that you have to make some domain information to be able to get, okay, to be able to design these heuristic. Now let's do one more example, so yeah, we'll take an admissible case itself. So this is example 2. Okay, so we have S, again a very small example, SB, ABC, and you have a G like this. Okay, so there are 2 ways to get to G, and let's say this is 1, 1, 1, 2, 3, and okay, so here H is 1, the goal state anyway H is 0, and here you have H is 4. For B you have H is 1, and for S you have H is 2. Okay, so here this is admissible now, right? So let's just check. So the goal state anyway, the distance is 0, the true distance is 0 and H is 0, it's fine. For C, the true distance to the goal is 3 and you have H is 1, that's okay. Now from A, the true distance is this sum, right? The true distance to a goal, there's just one goal, and the true distance is 1 plus 3, 4, and the heuristic is saying it's 4, it's okay. Now for B, what happens? You have 5 and the heuristic is giving you 1, so it's okay. And even for S, it's fine. Okay, you can check that. So this is admissible. Now here, let's just check what happens in the queue. Okay, so I'm running out of time. Is it okay if I take a few minutes to just finish this example?
Yes, ma'am.
Yes. Okay. So right. So okay. So we start off with S. S is visited. Okay. So we'll just mark this as visited, and then we have A. And what is going to be the cost? The total priority. So
5.
it's 5, right? 5, and you have SA, and then you have B, and here it's going to be 2, right? And SB, right? And then you will remove B, right? B is going to be the next. And what's going to happen? The queue will have A, 5, SA, and this is one neighbor. So C, what's going to be the total value, the total priority?
4.
4, and you have SBC. Okay, and you're going to pop C. Okay, and there's just one neighbor, so you only look at the outgoing neighbors, right? You don't look at incoming nodes. So next state is going to be A5SA. The queue is going to have what's next? What's the next entry?
G.
G with a priority
6.
6, and the path is S, B, C, G. Okay, and now you're going to remove A. Okay, so A is going to get marked as visited. Now what happens? There is a neighbor which is C, but it was already visited. So you're not going to push C into the queue. So what the queue had was just S, B, C, G. And you're going to pop this, and G is going to get visited. You're going to incorrectly get this path S, B, C, G, whereas there was a shorter path 3, 4, 5. Okay, you got a path of length 6, but actually there was a shorter path. So this is not enough. Admissible is not enough. You need something more. And that is a property which, I'll do it in the next class. So it's called consistency. The metric also has to be consistent. Okay, so yeah, there is some issue when you compare these three nodes. Like for example, here you have A, C, and G. Okay, so what the heuristic is telling you, this cost is actually 3. C to G is 3, but the heuristic is telling you that the cost is 1. And this cost, we know this is 1. This is the true cost. And the heuristic is telling you that to go from A to G, the cost is 4. Okay, so this is not correct, right? It's not consistent with itself. So if you go via C, the shortest path is 2. I mean, if you go via C, the path from A to G, even via the heuristic, it is going to be 2. But now the heuristic told you that it is from A to G, it is 4, right? So this is a problem. It's not consistent with itself. And we'll see how to resolve this and what is a property that needs to get satisfied. Okay, we'll see this maybe in the next class. Okay, so I think I'll stop here and take any questions if there are. Otherwise, yeah, we'll see you next week. And if you have any questions, you can drop by for the lab session. Okay, yeah. So thanks everyone.